Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 8, Lesson 12 on quadratic word problems. All right, so we've been doing this entire unit has been on polynomial algebra and ways to solve polynomial equations, especially quadratic equations, ones where the highest power is equal to 2. Now we're going to dive into some word problems that are going to allow us to use those skills. Quadratic word problems. There are many real-world scenarios that can be modeled with quadratic equations. These equations can then be solved by either completing the square or by factoring. So let's jump into one right away in exercise number 1. Consider a rectangle whose area is 72 square feet. We know that the length is 10 feet more than twice the width. We would like to find the dimensions of the rectangle. Letter A. If we represent the width of the rectangle using the variable w, then write an expression for the length of the rectangle L in terms of w. In other words, right, I don't want to bring in both a w and an L. Not yet, especially because they told me that the length is 10 feet more than twice the width. So in letter A, I just want you to basically say, okay, if w is the width, then what would the length be, right, in terms of w? Write down an expression for that. It should be pretty easy. Well, if it's 10 feet more than twice the width, then 2w plus 10 is the length. Whoops, don't know how that happened. And let's try that again, is the length. Okay, great. All right, letter B. Set up an equation that can be used to solve for the width w based on the area. All right, well, let me just remind you that the area of a rectangle is length times width or width times length. See if you can now set up an equation in B. Don't worry about solving it. Just set up an equation that can be used to solve for the width. All right, well, we know that width times length equals area. So therefore, w times 2w plus 10 must be equal to 72. All right, that equation models everything that the problem has told us. Now, of course, we want to try to solve it. Letter C. Solve the equation to find both dimensions. Why is one of the solutions for w not viable? And we'll talk a little bit more about what the word viable means in just a moment. But first, let's rewrite that equation down here. W times 2w plus 10 equals 72. Now, let me remind you of something. There is nothing called the 72 product law. So even though I've got a product here equal to 72, I can't take this set this equal to 72 and this equal to 72 and solve. That doesn't work. There's a zero product law, not a 72 product law. So let's solve this one together, right? What I'm going to do to begin is I'm going to distribute the w, giving me 2w squared plus 10w equals 72. Now, on the premise that I'm going to use the zero product law to solve this instead of completing the square, what I'd like to do is get this entire equation equal to 0. I can do that pretty easily by subtracting the 72 from both sides. Now, on the left-hand side, right, nothing combines with the 2w squared, nothing combines with the 10w, and really we're just then subtracting 72 and getting that equal to 0. All right? So this is the equation I now want to solve, okay? And I'm going to solve it using factoring. But before I do that, notice that the 2, the 10, and the 72 all have a common factor of 2. When that happens and I've got an equation set equal to 0, I've got two choices. I could factor the 2 out as a GCF, or I could divide both sides of the equation by 2. And that's what I'm going to do in this situation. Both work absolutely fine. You could factor or you could divide. But I'm going to divide both sides of this equation by 2, all right? And remember, you have to distribute the division. So I have 2 divided by 2 times w squared plus 10 divided by 2 times w minus 72 divided by 2, and 0 divided by 2 is 0. This then results in w squared 5w, and negative 36 equal to 0. Okay? I finally am at a point where I was at in various problems over the past few lessons where I can now solve this equation by factoring. Could I solve it by completing the square? Sure, but that would require me to divide 5 by 2, which would give me 5 halves, and then square it and add it on, and right away, I don't want to do that. What I'd like you to do now is pause the video and solve this equation by factoring. Take a moment to do that. All right, so I'm looking for two numbers. This is a trinomial, right? Just straight up trinomial factoring. I'm looking for two numbers whose product is negative 36 and whose sum is positive 5. Obviously, that means one number must be negative, one number has to be positive, and the number that has the larger absolute value has to be positive for the net sum to be positive. Wow, that's a lot of ways to basically just say that the two numbers are positive 9 and negative 4. All right, so up here, I'm going to factor that as w plus 9 times w minus 4 is equal to 0. I can now take w plus 9 and set it equal to 0, w minus 4 and set it equal to 0. I'll subtract a 9 from both sides and I'll get w equals negative 9. And I'll add a 4 to both sides and I'll get w equals 4. In all word problems, you always want to be very aware of things like units and stuff like that. So if I go back up here, right, I note that my rectangle has units of 72 square feet, which means that my width must be in terms of feet. Therefore, these two answers are negative 9 feet and 4 feet. Okay, so, right, what is the correct answer? Well, part of this problem asked us to discuss why one of the two solutions is not viable. Viable means it's something that could be used, it's something that's possible, etc. It hopefully makes sense to you that a rectangle cannot have a width that is negative, right? So I'm going to write down right now that this is not viable because width cannot be negative. Many quantities can be negative, temperature is one of them, but width cannot be negative. And therefore, my final answer, right, the width of my rectangle is 4 feet. All right. Had they also asked for the length of my rectangle, I would then want to go ahead and figure that out. But the problem just asked me, oh, it actually did say solve and find both dimensions. I apologize, right? I've got to find both dimensions. That's easy enough. Let's go on and find the length. Remember, the length is given by this particular expression, right? The length is given by 2w plus 10, and therefore, the length is equal to 2 times 4 plus 10, which is equal to 18 feet. I almost forgot to do part of the problem. All right, so we have a width of 4 feet and a length of 18 feet. Now, area and geometric properties in general give us many different examples of where we can have quadratic equations come up in word problems. So let's take a look at another one that's a little bit more complicated. When we know the perimeter and the area of a rectangle, we can model the situation with a quadratic equation that allows us to determine the dimensions of the rectangle, which is kind of cool. If I gave you the area of a rectangle, like if I said the area of a rectangle was 20 square feet, right, you would never know what the length and the width were because they could be 5 feet and 4 feet or 2 feet and 10 feet, right? Likewise, if I gave you the perimeter of a rectangle, it wouldn't be enough to know the dimensions. But interestingly enough, if I give you both the area and the perimeter, that's enough to be able to figure out the dimensions of the rectangle. So let's look at a situation like that. These are a favorite of state assessments, right? They give you the area, they give you the perimeter, and you've got to figure out the two dimensions. Let's take a look. A rectangle has a perimeter of 48 feet and an area of 135 square feet. Letter A, choose appropriate variables for the length and the width of this rectangle and label on the diagram. All right, well, I want us to all do this sort of in the same way, if you will. So let's do the most logical thing ever, and let's call the width W, and let's call the length L. All right, just that simple. okay? Now, we want to write a system of equations based on the information given, all right? See if you can write down two equations, one equation that involves the perimeter, one equation that involves the area, and both equations will involve the W and the L. Pause the video now and see if you can do that. All right, well, the perimeter equation is always the same. It is always twice the width plus twice the length is equal to the perimeter. And the area equation is also always the same. The width times the length is equal to 135. Don't worry about putting the units right now. There's no real need to do that, okay? We just need those raw numbers. 2 times W plus 2 times L equals 48, and W times L equals 135. All right, let's take a look at letter C. Using substitution, solve the linear quadratic system from B to determine the dimensions of the rectangle. All right, now this is a little bit trickier, okay? Because in order to solve a system by substitution, we need one of these equations to have one of the two variables isolated, all by itself, okay? And what I'm going to do, and some teachers may choose to do this differently, by the way, I'm going to take this first equation and I'm going to solve it for either W or L. It doesn't matter which one. It's totally irrelevant, okay? I'm going to solve it for either W or L, and then I'm going to substitute it into the second equation. Okay, so let's start with that process. I'm going to take this thing down here. All right, and I think what I'm going to do is I'm going to solve it for L. So I'm going to subtract a 2W from both sides. Okay, and that's going to give me 2L is equal to 48 minus 2W. Now again, my purpose in doing this, I want to be very clear, is so that I can eventually substitute my result into that area equation. I'm going to divide both sides by 2. Remember, division distributes, so 48 divided by 2 is 24, and 2 divided by 2 is just 1. So I find that my length must be 24 minus my width. Okay, now again, I did all of that simply so I could substitute this now into this equation, okay? But let's do that. That shouldn't be that bad, right? I'm now going to substitute this into my area equation, and that's now going to look like, let me try to keep that on the screen, W times 24 minus W is equal to 135. And now we really have a situation that's very similar to that first problem that we worked on, okay? So what I'd like you to do is take a moment, actually maybe quite a few moments, and see if you can solve this equation for W. Keep in mind there is no 135 product law, okay? Just like before, we'll want to multiply it through, we'll kind of want to get everything equal to 0, etc. You may want to use factoring, you may want to use the difference of, not the difference of perfect squares, you might want to use completing the square, that's up to you. But see if you can solve this equation, and then we'll go through it. All right, well this is certainly more challenging than the last one. Okay, I'm going to move this out of the way, give myself a little bit of extra room. Let's do it. So the first thing I'm going to do is distribute the W. That's going to give me 24W minus W squared is equal to 135. Now, one thing I do not like is having a negative W squared here. I can get rid of the negative attached to the W squared in one of two ways. I can either divide both sides by -1, or I can move everything to this side of the equation. Now that works because when I move that negative W squared over here, I have to add it. Now granted, I then have to subtract 24W, and that looks a bit confusing, but keep in mind that none of this stuff can be combined. So I'm simply going to have W squared minus 24W plus 135. Okay, great. Now we've got a choice. We can either factor this thing and use the zero product law, or we can use completing the square, which wouldn't be too bad because our coefficient here is 24. It's even. Well, it's negative 24, but it's still even, right? And in fact, I think I'm going to take advantage of this situation right now to review completing the square. Now, ironically, with completing the square, what I kind of want to do is I want to move the 135 over to this side. By the way, factoring works just fine. Okay, but it's been a little while since we've completed the square, so I'd like to actually do that. And I'm going to bring this equation all the way up here just so that I've got a little bit more room. Now remember, completing the square, I'm going to look at this particular number, negative 24. I'm going to divide it by 2, which is negative 12. I'm going to square it, and I'm going to get 144. So what I'm going to do is I'm going to add 144 to both sides of this equation. And maybe I'll move that out of the way. Now at this point, that means that the thing on the right-hand side is a perfect square trinomial, which it is. It's w minus 12 squared. On the left-hand side of the equation, I've just got the number 9, which is really rather nice, right? Easy to work with. Okay, I can now take the square root of both sides. That will give me w minus 12 is equal to plus or minus 3. So if w minus 12 is equal to 3, and w minus 12 is equal to negative 3, I can go ahead and solve. In which case, I'll get w is equal to 15. Got to move that out of the way again. Add 12 to both sides here. And I get w is equal to 9, which is interesting. You know, in the last problem when I solved for w, I had one answer that was positive, I think it was 4, and the other answer that was negative, I think it was negative 9, and we threw the negative 9 away because it just wasn't viable. In this case, both of these things are completely good, right? 15 is good and 9 is good. So which one's correct? Right? That's a real conundrum, right? Is it going to be 9? Is it going to be 15? Well, before I make that decision, let me figure out what the length is. Okay? Now keep in mind that the length is 24 minus the width. The length is 24 minus the width. So let's figure out what the length is in this situation. All right? So the length is 24. Come on. Oh, come on. There we go. 24 minus the width. So 24 minus 15 is 9. And here, the length would be 24 minus 9. So the length would be 15. Now take a look at these answers. In one case, the width is 15 and the length is 9. And in the other case, the width is 9 and the length is 15. This doesn't surprise me at all, right? And it doesn't surprise me because W and L are just letters that we use to stand for the two sides of this rectangle. We didn't say this one has to be the longer one and this one has to be the shorter one, so it kind of makes sense that we get this symmetry. And the plain fact is, at the end of the day, it doesn't matter which one's the width and which one's the length. Convention says that the length is the longer of the two dimensions, but it really doesn't matter. The two dimensions of this rectangle are, let me just make sure I got my units right, 9 feet and 15 feet, right? And that's really it. Use substitution, determine the dimensions of the rectangle, and the dimensions are 9 feet and 15 feet. Which one is called the width and which one is called the length is completely irrelevant. But that can be really tricky for students because you get down to this point and it's like, well, is the width 9 or is the width 15? And the interesting thing is, well, if the width is 15, the length is 9, and if the width is 9, then the length is 15, and either way, this is a 9 by 15 rectangle. All right, let's do a little bit more work, but maybe with some problems that don't involve area. Now, sometimes we're going to model situations that just involve numbers, and they're not related to real-world scenarios at all. Information about products of numbers often leads to quadratic equations, and man, can that information be confusing. So let's take a look at one that just looks kind of crazy. Let's take a look. Two integers have the following property. When the product of one more than 3 times the number with 2 less than the number is found, it is equal to 43 more than the number. Find the two integers that fit this description. Now, one thing that I just want to mention in this is the point here is that there are two integers that make this true, okay? Two different numbers that when the product of one more than 3 times the number with 2 less than the number is found, it's equal to 43 more than the number. Find the two integers that fit this description. Well, let's do this. Let's let n be equal to an integer. What I'd like you to do is take a moment and see if you can translate this gobbledygook, okay, into an equation that can be solved. Take a moment to go ahead and try to do that. All right, well first, let's just be very careful. Product means we're going to have a times, right? That's going to be a multiplication, all right? 1 more than 3 times the number. 1 more than 3 times the number. That's 3n plus 1 with 2 less than the number. That's n minus 2. Okay, so before we even go on, right? 1 more than 3 times the number, 3n plus 1. 2 less than the number, n minus 2. And it's a product, right? When that is found, it is equal to 43 more than the number, which has to be n plus 43. Right, nice and slow. 3n plus 1 times n minus 2 must be n plus 43. And now we have to solve this. Now, this is interesting. This is the first time we've seen this come up in any kind of quadratic problems. We're going to actually have to multiply this out, right? Then we're going to want to get it all equal to 0 and then probably use the zero product law. Or we might use completing the square. First thing I'd like you to do is pause the video and just multiply this out. Use FOIL, use double distribution, use whatever you want, but figure out what that left side is equal to all multiplied out. Pause the video now and go ahead and do that. All right, here we go. I'm going to use FOIL, so I'm going to do first. It's going to be 3n squared, outer, negative 6n, inner, plus 1n, last, minus 2, equals n plus 43. Not doing anything with that yet. 3n squared minus 5n as I collect those like terms, minus 2, equals n plus 43. Okay. Now at this point, we've really got an equation that is similar to something that we solved a few lessons ago, right? I would suggest trying to use the zero product law to solve this. I'd like you to pause the video now. First things first, get everything over on one side of the equation, probably on the left-hand side, and get that equation equal to 0. Then try to use factoring to solve for those 2 integers that satisfy the description of this problem. Pause the video now and see if you can finish this problem out. All right, here we go. Extend my page a little bit, give myself a little more room. I want to get everything equal to 0, so I'm going to subtract an n and a 43 from both sides. Nothing combines with that 3n squared. Negative 5n and negative 1n is negative 6n. Negative 2 and negative 3 is negative 45. That's equal to 0. Notice that the 3, the 6, and the 45 are all divisible by 3. So I'm going to go ahead and just divide both sides of this equation by 3. Now remember to distribute that division. 3 divided by 3 is 1n squared. 6 divided by 3 gives me that negative 2n. And 45 divided by 3 gives me 15, or negative 15 equals 0. I now have a beautiful trinomial that I can solve by factoring. That's going to be n minus 5 times n plus 3. Then I can take n minus 5 and set it equal to 0. N plus 3 and set it equal to 0. Add 5 to both sides. That's going to give me n is equal to 5. Subtract 3 from both sides. And that's going to give me n equals, whoops, negative 3. I don't want you to think it's negative 0.3. And those are my 2 integers, right? Both of which are completely viable, right? There's nothing in this problem that says it's got to be a positive number, right? So both n equals 5 satisfies that original equation, as does n equal negative 3. It's pretty hard to see that negative. Let me try to draw it in a little bit darker. There we go. All right, let's do another one that's got some just numbers in them. All right, here we go. Quadratic equations arise when working with consecutive integers. Be especially careful with your use of parentheses when you model these problems. If you've got a binomial, get parentheses around it. It can't hurt. It just can't hurt, right? So be careful there. Let's talk about exercise number 4. Find all sets of two consecutive integers such that their product is 8 less than 10 times the smaller integer. All right, consecutive integers. Remember we had consecutive integers, consecutive evens, and consecutive odds. Consecutive integers just differ by 1 each. So we should lay out some let statements here. I'm going to let n be equal to the smaller integer, and I'm going to let n plus 1, oh, that was supposed to be a plus 1, equal the larger integer. Now remember, if these had been consecutive evens or consecutive odds, then I'd have n and n plus 2. If there had been a third one, I may have even had n plus 2, n plus 4. If it's just consecutive integers, it'd be n plus 1, n plus 2, n plus 3, etc. All right, now I need to set up an equation with these two. I'd like you to pause the video and see if you can model the information they gave you in this problem based on this, and right away, I'm slapping some parentheses around that. You know, just get them in there. Take a moment and see if you can set up the equation. All right, well, it says that their product, let's get that down right away, n times n plus 1. It's really, really important that you know the word product means to multiply. Their product is oftentimes translated in math as equals. Their product is 8 less than 10 times the smaller integer. So if I take 10 times the smaller integer and I subtract off 8, then I've got 8 less than the 10 times the smaller integer. Make sure you don't have 8 minus 10n. That is a completely different thing, and it will give you a completely incorrect answer. All right, it's now time to solve this. You want to begin by multiplying first through on that left-hand side by n, and then proceeding from there. Pause the video now and see if you can find all sets. There's going to be two different sets of two consecutive integers that make this true. All right, let's go through it. So we've got n squared plus n, once I distribute, equals 10n minus 8. I think I'm going to get everything equal to 0, so I'll subtract a 10n and add an 8 to both sides. I think I'll put my result up here. That's going to be n squared. N minus 10n is negative 9n. And we've got nothing that combines with that positive 8, so we're just here. I now need to factor this trinomial. This one's a little bit weird. I'm looking for two numbers that have a product of positive 8 and a sum of negative 9. And those would be negative 1 and negative 8. Solving this, n minus 1 is equal to 0, and n minus 8 is equal to 0. Add 1 to both sides, and I'll get n is equal to 1. Add 8 to both sides, and I'll get n is equal to 8. Now keep in mind, right, they said find all sets of two consecutive integers. Well, that's actually easy now, because those two sets then would be 1, 2 and 8, 9, right? Those are the two that have the 1 in them, right? 1 and 2, and then 8 and 9. Okay, let's do one more problem. Here we go. Exercise number 5. Brendan claims that the number 5 has the property that the product of 3 less than it with 1 more than it is the same as 3 times 1 less than it. Show that Brendan's claim is true and algebraically find the other number for which it's true. Okay, so there's really two big pieces of this problem. One of them is just verifying that what Brendan claims about the number 5 is actually true. The second piece is setting up an equation to try to find another number that it's true for. So first things first, pause the video and see if you can just show that what Brendan claims about the number 5 is actually the case. Take a moment to do that. All right, so what did Brendan claim about the number 5? The product of 3 less than it, so let's see, 5 minus 3, with 1 more than it, so that would have to be 5 plus 1, is the same, equals, as 3 times 1 less than it. 3 times 1 less than it. So this is what we're really kind of checking to see in terms of Brendan's claim. All right, well, let's see. 5 minus 3 is 2. 5 plus 1 is 6. And then, of course, that would be 3 times 4. 2 times 6 is 12. 3 times 4 is 12. Brendan's claim is correct. All right. Now, the second part of this problem is to find the other number for which this is true. In other words, there's some other number where 3 less than it times 1 more than it is 3 times 1 less than it. Okay, there's some other number, right? Now, it's kind of cool because we could say, well, let's let n be equal to the number. All right, we want to set up an equation now. We want to set up an equation now that will allow us to solve for n. See if you can set up that equation. Pause the video right now. Well, quite frankly, we sort of already have the equation. It's right here, except we just need to put an n in wherever there's a 5. So we're going to have n minus 3 times n plus 1 is equal to 3 times n minus 1, right? I mean, that's exactly what it says, right? The product of 3 less than a number, right, with 1 more than a number is equal to 3 times 1 less than the number. All right, now we have to solve this. And this is going to be a little bit of a beast because the first thing we need to do is multiply that out using FOIL or whatever. Multiply this out by just using single distribution. Get everything equal to 0. Use factoring or whatever to solve it and try to find that other number. So I'd like you to pause the video now. This may take you up to like 5 or 6 minutes to do and see if you can figure out what the other number is. All right, let's do it. Here we go. So first things first, I'm going to multiply this out, right? N times n is n squared. N times 1 is n. Negative 3 times n is negative 3n. And negative 3 times 1 is negative 3. On this side, I distribute that 3 through, and I get 3n minus 3. Collect like terms on this side. N squared minus 2n minus 3 is equal to 3n minus 3. All right, so that's where I'm at this point, right? I still need to get this equation equal to 0 if I want to use factoring to solve it, which I think I'm going to go with. To do that, I'm going to subtract a 3n from both sides and add a 3 to both sides. And something kind of weird happens there. All right, negative 2n and negative 3n is negative 5n, but here a negative 3 and a positive 3 cancel, so I just get n squared minus 5n is equal to 0. All right, I certainly want to solve this using factoring and not completing the square. So all I can do is factor an n out of this. So I get n times n minus 5 is equal to 0. All right, that means now, according to the zero product law, I can get n equals 0 and n minus 5 equals 0. This one I can solve by adding 5 to both sides, and I get n equals 5. So what's the other number that fits this description? Well, it's n equals 0. What about the n equals 5? Well, that one I already knew, right? Because I was told that that one worked. We verified that that one worked. So actually, if I didn't get n equals 5 out of this, I would have been pretty surprised. All right? So n equals 0 is our other number. Let's wrap this up. Now, there are tons of different modeling problems that you could do that would result in a quadratic equation that you have to solve. These are just some of them, right? Many times, quadratic equations come from information about area and perimeter. Other times, it's just simply, as we saw, descriptions of numbers that fit particular patterns, right? And to weed through those patterns can be very, very challenging. So make sure to really take some time on the homework. It's a lengthy, lengthy set of problems that you'll probably take a while to go through with your teacher, okay? There's nothing like kind of working through many word problems to really kind of give you a workout using things like factoring and completing the square to solve quadratic equations. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.